in the cloud. Okay, good. So let's start. So it's my big pleasure to introduce Christian Urech from University of Lausanne. EPL. Sorry, yeah. And Christian will talk about actions of Cremona groups on KT0 cube complexes. Thank you, Christian.
Thanks a lot, Vanya. And thanks a lot for the opportunity to speak here. So I enjoy this seminar a lot. Also, like all the YouTube recordings are always great to have a look at. So yeah, I will talk about actions of Cremona groups on KT0 cube complexes. So this is joint work with Anne Lanchou from Université d'Orsay. So here we have X variety over a field K. So here K really can be any field. So usually if you do things in that generality, either it's technically very complicated or it's just some easy things that work for everything. So in this case, we are rather in the easy case where it works for all fields. And now to this variety, we can associate the group of birational transformations. And if X is a rational variety, then it's called the Cremona group, named after Luigi Cremona. But in this talk, we will really work over arbitrary varieties. So as we know, these groups, they have been studied since more than 150 years, and there are always new surprises coming up. And like 20 years ago, maybe it started that people started looking at these groups from the perspective of geometric group theory. And actually, it's very interesting. It's also nice for geometric group theory because it gives very nice examples of groups acting on geometric spaces, but also it gave us many tools to understand the Cremona groups. So in this work, we kind of continue this tradition and we look at another tool from geometric group theory, which are these KT0 cube complexes, and we apply them to study Cremona groups. So maybe let's start with a very elementary observation. So if we have that, we have a variety Y and we have a birational map to our variety X, well, then we can just conjugate the automorphisms of our variety Y and we get a subgroup of Brx. So such a birational transformation gives us, birational map gives us an embedding of the automorphism group of Y into the group of birational transformations of X. Okay, so this leads to the following definition. So we say that an element F in the group of birational transformations of X is called regularizable if there exists a variety Y such that F is conjugate to an element, like to an automorphism of Y. Now, if this variety Y can even be chosen to be projective, then we call our element F to be projectively regularizable. Now, maybe the first naive question would be like, are all elements in Brx regularizable? So that we always find some kind of variety, not necessarily complete, where it acts as an automorphism F. But of course, that's not true. Let's just look at the example F that maps a point xy to, for example, like birational transformation of A2 to x plus 1. Then we can look y divided by x. And this element is not regularizable. So why is it not regularizable? Well, we can just look at, if we iterate f n times, so this maps the point xy to the point x plus n, and here it's y divided by x times x plus 1, etc. times x plus n minus 1. So basically, the exceptional divisor of f iterated n times has n irreducible components of codimension 1. And now this implies, of course, that the f cannot be regularizable because, well, otherwise, if we have that, so if there exists a g in some automorphism group of Y, and then we have a rational transformation from Y to our variety X. And then we look at the exceptional locus of phi g iterated n times phi inverse. Then we see, okay, I mean, since this automorphism doesn't contribute to the exceptional locus, so the irreducible components of this exceptional divisor of codimension 1, they are just given by f inverse and phi inverse and phi. So their number has to be bounded, which is not the case for this transformation. Yeah, so let's make this just as a small observation to start the talk. So if f in Urech is regularizable, then the number of irreducible components of codimension 1 in the exceptional divisor of f iterated n times has to be uniformly bounded for all n. And I mean, we can make a very similar argument if S is a projective surface or a regular projective surface. And if our F is a projectively regularizable, then, well, the number of base points of F iterated n times still has to be uniformly bounded, because, again, with the same argument, if we can conjugate it to an automorphism, okay, there's only base points that are added by the map that conjugates our transformation to an automorphism. And so this kind of like our cube complex kind of will show us like how to embed these various automorphism groups of all the varieties that are rational equivalent into our groups of rational transformations. And in particular, we will also see that here the converse is true as well. Okay, so we will, during this talk, actually construct quite a few cube complexes. So in our work, we constructed quite a few cube complexes. So I would like to, first let me say what is a cat-zero cube complex. So we all know what a cube complex is. So it's just a polyhedral complex made out of cubes. So basically we take Euclidean cubes of arbitrary dimensions and we glue them together along their faces. So for example, we can look, I don't know, if we can take here some 3 cube. So that's a solid cube with its faces, and then we can, I don't know, glue here a 2 cube and here a 1 cube, something like that. But also, like, we don't have to fill the cubes. We could have something like I don't know, construct some kind of a hollow cube, or of course also graphs. I mean, every graph is a cube complex, and it's just a cube complex consisting only of 1 cubes. Okay, so cube complexes, we know what it is. Now we have to say what is cat-zero. So for this, I quickly make a definition. Just to recall, what is the link of a vertex in a cube complex? So if L is a cube complex and V a vertex of this cube complex L, then we define the link of this vertex V to be the simplicial complex whose vertices are the vertices of L that are adjacent to V. And then to a set of n+1 of these vertices in our that are adjacent to L, we fill them in with a simplex. If well, if we add V to this, that these all belong to a cube in our complex L. Maybe let's make some examples. So, for example, if here, I don't know, we can choose this to be our vertex V. So now, okay, so our elements in the link are now, or maybe that's not well chosen because we don't see what happens. So let's maybe rather take this one as our V. So then we have this point, this vertex, and this vertex. So these 3 vertices are contained in our link. And now, okay, we see they are pairwise connected because they are all contained in the squares. And then also all the 3 are contained in 2 simplex because they all belong to a solid 3 cube. So our link here is this one. this simplicial complex. Now here, if we take the vertex V to be here, I mean, we still have here one element, one vertex, and here one vertex in our link, and they are still pairwise connected. But since the cube, they don't belong to a bigger cube, this stays hollow. And I mean, here, if we look at I don't know, this vertex here, well, we just have these two vertices in the link, but they are not connected because they don't belong to a square. Okay, so this is the link. Now I need to say what is a flag. What is a simplicial complex that is flag? So a simplicial complex is called flag if every finite set of pairwise adjacent vertices spans a simplex. So if we have a set that is pairwise connected, then we want that is filled by a simplex. Basically, we want that there are no empty or hollow simplices. So for example, this one here, this one is flag. This one here is not flag. And this one here again is flag. Okay, so these are flag. And now we can define what a cat-zero cube complex is. So a cube complex is called cat-zero if it is simply connected and if all its links are flag. So basically, let's look at this example. So here we see that this one is, okay, we see that here the links, if we draw them, they are all flag. So this one here is cat-zero. So this one here is simply connected, but here it has a link that is not flag. So this one is not cat-zero. So for this one, all the links are flag, but it is not simply connected. So it's also not cat-zero. So in some ways, how to think about it is like cat-zero is like a very weak form of a non-positive curvature. It's like a form of non-positive curvature. So basically, it can be flat. I mean, cubes are flat, but it can also be negative, like depending on how you glue the cubes together. But it shouldn't be like, we shouldn't have positive curvature. So in some ways here, this is like local positive curvature. So this definition of not of all links being flag, that's like a local condition, and the simple connectedness is a global condition. And if both of these are satisfied, it's cat-zero. Now, maybe some of you know what cat-zero means in a metric sense. So we'll just take this as a definition here as cat-zero, but it's actually for cube complex, it's the same. So that's the famous theorem by Gromov. So I think for finite dimensional cube complexes, and Leary showed it in the general case, is that actually, if we have a cube complex, we can look at the Euclidean metric on this cube complex. And this one is cat-zero in the metric sense if and only if the cube complex satisfies this condition. So the Euclidean metric on a cube complex L is a cat-zero if and only if the cube complex L is cat-zero. So cat-zero in the sense we defined it. So actually that's good. But okay, we will not use this Euclidean metric. We will always work in this talk with the combinatorial distance on our cube complex. Okay, but now we would like to construct the cube complexes with actions of Cremona groups. So the first cube complex I would like to construct is the so-called blow-up complex. So in some ways, I would say this is the most beautiful cube complex of all the cube complexes we will encounter today. But the drawback of this cube complex is that it only works for surfaces. So the results we will find for Cremona groups have mostly already been known. However, it gives like a nice framework. First of all, it generalizes them for arbitrary fields, and most of these results have only been proven for algebraically closed fields. And also, second of all, it simplifies the proof and it gives a nice perspective. And then later on, we will look at more general cube complexes that work in any dimensions. Okay, so for this, we look at S. It's a regular projective surface, again, over any field K. Now, let's construct this cube complex. So we define a marked surface. So we look at marked surfaces. So these are just surfaces together with a birational transformation to our fixed surface S. So this is just a couple T and phi, where T is a projective regular surface, and phi from T to S is a birational transformation. Okay, and now the vertices of our cube complex, these are just these marked surfaces, but up to isomorphism. So these are equivalence classes of marked surfaces. And we say that the marked surface T and phi is equivalent to the marked surface T prime phi prime. Well, if the birational transformation phi prime composed with phi inverse, so that's a birational transformation that goes from T prime to T. So if this is an isomorphism. Okay, so we have the vertices of our cube complex. So in the next step, we would like to define what are the edges, so the one cubes. So, and the edges basically are just blow-ups. So we say that our vertex, so T prime phi prime, is connected by an edge to our vertex T phi. If if this basically this the connection between those two is given by a blow-up of a closed point. So we want that the map phi inverse composed with phi prime going from T prime to T. So if this birational transformation is actually birational morphism, and it is the blow-up, or is a blow-up in a closed point. And here the nice thing is also this gives us an orientation, so we can give a direction to all the edges. So we say here we orient it from the bigger one to the smaller one. So we have, this gives an orientation on this cube complex. Now, okay, now we can continue like that. Basically, that's instead of just blowing up one closed point, we can now blow up many closed points, and this gives us the n cubes. Let me explain this briefly. So the n cubes are now just defined. Well, now we just repeat this. So if we have here our surface T, then we can blow up a closed point P, for example. So we get the surface TP phi P. Here we can blow up another point Q phi Q. But then, of course, once we are here, we can still blow up the closed point P. And here we can still blow up the closed point Q. So the order doesn't matter here. So no matter we get to TPQ, phi PQ. And now whenever we see such a n cube, like the skeleton of an n cube, we just fill it in with a cube. So okay, then this week we can continue, of course, also with 3 points and with arbitrarily many, and always when this happens, we fill in the n cube. And this defines us our cube complex. So maybe just the first remark is maybe like, okay, this cube complex in some ways it's very large. Like we could, like the cubes can become arbitrarily big. So it's not a finite dimensional cube complex. It's also not a locally finite dimensional cube complex, because as soon as we have a surface, we have infinitely many closed points, and we can take as many of them as we like and blow up one after the other, and we get a cube of any dimension. Then maybe the next next question one could ask is this cube complex connected? And here the answer is yes, because we have the theorem of Zariski, the factorization theorem. So if we have two regular projective surfaces and a birational transformation between them phi, then we can always factorize this birational map into a blow up of closed points and blow down of closed points. So this means that we can connect any two marked surfaces just by going up and blowing up closed points. So this gives us that our cube complex is connected. Let's maybe make an example to illustrate this a bit. So here I have a nice image. Let's look at sigma, so the standard quadratic involution from P2 to P2 that just maps a point x, y, z to 1 divided by x, 1 divided by y, 1 divided by z. So just to recall, I mean, that's the birational transformation that's given by, well, we have 3 base points, we blow them up. So we get here to our Pezzo surface, and then we blow up, we contract the other, like we contract these 3 lines, and we get down here to P2 again. So what happens on the cubical level? So here we have our P2, and let's mark it with the identity. So we start with the identity. So we can blow up a point, our first base point here, then we blow up the second base point and the third base point. So here we arrive at this surface, so this Pezzo surface. And of course here we could also first blow up the other one, and then blow up this one, and then blow up this one. So the order doesn't matter. So that's why we have a cube here. So we get here. And now starting from here, we can contract the curves. Of course, here we could have not contracted those curves, but once we are up here, we can contract them. And then we get again to P2. But here now with the marking sigma. So basically that's a small thing. Now it gets higher dimensional, it gets a bit more complicated to imagine this. Maybe just a remark, like these cat-zero cube complexes, they have been quite popular, like they've been introduced, for example, in genetics. If you look at a gene sequence and then you look the ways these genes can change. So here you can just think of like each time you change a gene, and once you change it, then you have maybe newer ways to change it, but some other changes if the order doesn't matter. So this that's one place where these cube complexes appear. Another one is robotics. We have a robot arm, and it has various ways where it can move to. And then if you move here or here, then maybe the order doesn't matter. You can move here and then here. And then you get a cube complex, and you can study the geodesics. So basically now here we take the same idea from genetics, but instead of looking at gene mutations or changing the genes, we just blow up our surfaces. So in some ways we also mutate our surfaces, and we similarly get a nice cube complex. Now the theorem that we showed with An is that this cube complex is cat-zero. So how do we show that it's cat-zero? Actually, it's not very difficult. So the basic idea, I'll just give the idea, is I mean, to show simple connectedness, I mean, if we have a loop in our cube complex, okay, we can assume that it always walks along the edges, so the one skeleton. And now we just find one surface that dominates all these surfaces that appear on this loop. And then you can show that actually you can just contract the path all the way to this point up here. And to show that the links are flat, well, that almost follows from the definition because we just filled in all the cubes that we found. And then, okay, the way this cube complex lives, it's not so difficult to show that it is actually also, all the links are flag. Okay, so we have a cat-zero cube complex. And now, of course, what is important is that the group of birational transformations of our surface S acts on this cube complex by isometries. So how does this how does it act? So if we look at f of t phi, well, this is just we just look at the action on the marking. So we just say this is t, and now the marking changes. So it just changes the marking, and then this is clearly an isometry, and we also see that it preserves the orientation. So maybe one thing to mention is that in this talk, we always consider the combinatorial metric. Well, I already mentioned it, but to be sure again. When I speak of distance, then it is always the combinatorial distance. Okay, so let's make some remarks. So the first remark is, well, about the distance. If we look at the distance between two vertices, so one is represented by t and phi, and the other one is represented by t prime, phi prime. What is this distance? So this is just the number of base points of phi inverse composed with phi prime plus the number of base points of phi prime inverse composed with phi. So basically, if we have here our t and t prime, and they are connected here by phi inverse composed with phi prime. So basically, the shortest path is really to blow up all the base points and then contract all the and then have here all the blow-ups of the base points of the inverse. So this gives us exactly a good understanding of what the distance is. And the second direct observation is if you want to see what are the vertex stabilizers. So here we can observe that if we have a birational transformation of SF that fixes a vertex T phi. So this one is same as this one. So this is just T F phi. So by the definition of this equivalence, this is equivalent to saying that phi inverse composed with phi with F composed with phi is an automorphism of our surface T. So basically, we can see that the vertex stabilizers correspond to the automorphism groups. Okay, so now, so basically, as we have a nice cube complex, we understand the distance, then we understand the stabilizers of the vertices. So now maybe we should use that it is cat zero. So cat zero cube complex, they have many nice properties. So one of them is that the theorem by Haglund, that if we have an isometry of a cat zero cube complex that preserves an orientation, then it always has to be either elliptic, so this means it fixes a vertex, or it has to be loxodromic. This means it acts by translation along an axis. So again, here it's important that we work with the combinatorial metric. It's not true anymore for the Euclidean metric. Okay, so we take a combinatorial axis, and it's just translational. There exists an axis, and it's just translation along the axis. Of course, this axis is not at all unique. Like it could be, yeah, it could be flat, and it's just there are many parallel axes. Okay, so let's look at what this means for our elements in BRS. So we can now observe that, well, an element in BRS is elliptic, so means it induces an elliptic isometry on our cat-zero cube complex, if and only if, well, it fixes a vertex, which we have seen is equivalent to F being conjugate to an automorphism of a projective surface. So this is equivalent to F being projectively regularizable. And another nice thing is if the element is not projectively regularizable, then this means there exists an axis. So if F in BRS is loxodromic, and if we have y, maybe t phi that is contained on the axis, of F. Well, what does this mean? This means that, okay, we have here the y phi, then this is mapped by F to y f phi, and then y f square phi, etc. And then here we have a geodesic path. And now, since this is all on the axis, this means, like, I mean, the distance here is the same as the distance here, the same as distance here. So in other words, we have that the number of base points of phi inverse f iterated n times phi is just n times the number of base points of phi inverse f phi. And this is true for all n. And in other words, this is like one of the definitions of saying that f is this phi inverse f phi is algebraically stable. Is algebraically stable. So basically, this shows directly just this fact from cat-zero cube complexes that the element has to be loxodromic or elliptic, that we always can find a algebraically stable model for F. So okay, just like from this, we obtain the following theorem. If we have F in the group BRS, then there exists an algebraically stable model of F. So this is actually a result that has been already shown by Dillner and Favre. And then if we look at this, this limit here, like this is often called the dynamical number of base points. So the limit of the base points of F iterated n times divided by n. But for us, of course, it's just like the translation length in our cube complex, or a half times the translation length in our cube complex. So this always has to be an integer. And also the number of base points under iteration, well, either it is bounded or the growth has to be linear. So also this has already been known by, been shown by Blanc and Desserty. But again, like usually the papers are just phrased over the field of complex numbers or algebraically closed fields. And here it's kind of like very conceptually clear. It makes really, gives a geometric meaning to this length. It's, if we assume the results from cat-zero geometry, straightforward corollary. And it works for all fields. Maybe another result from cat-zero cube complexes is this theorem by Gerasimov. This states that if a group G acts on a cat-zero cube complex, and we assume that the orbit is bounded, and also we assume that G preserves an orientation, then G fixes a vertex. So that already it's not at all clear on a general geometric space, of course, if you have an action of a group G that that it has a fixed point. It's true for cat-zero space, but only if they are complete, and our space is not complete. But for if it's a cube complex and cat-zero, then it always has to fix a vertex. So again, we can have a direct corollary from that if G is projectively regularizable, now we know that this is equivalent to number of base points of f being uniformly bounded for all f in G. Because like that's exactly the condition for having a bounded orbit. So one example like to show this is actually also a nice result. We can look at if G is an algebraic subgroup of BRS. Well, then the number of base points is uniformly bounded. So we can apply our corollary and we obtain that actually G is projectively regularizable. And usually to show this kind of, or show this statement, one uses the regularization theorem of Weyl or together with the theorem of Sumihiro for on equivariant completions. But here actually it's nice we get without using these theorems from algebraic geometry, but just this action on the cat-zero cube complex, we can deduce this fact. Then there is another property. So a group is said to have property FW if every action of this group on a cat-zero cube complex has a fixed point. So it's a bit like a weaker version of Serre's property FA. And I mean, there are quite a few groups who have this property. So for example, maybe most prominently, if we look at SLNZ for n bigger or equal to 3, not for n equal to 2, but also all the groups with a property T and some other groups satisfy this property. So now again, from our construction, we get the direct corollary that actually if we have a subgroup in BRS that has the property FW, then we know directly that it is projectively regularizable. Again, this has already been known for, well, at least for algebraically closed fields. This theorem is due to the first case was by Julie Desarty, then by Serge Contat and Yves Cornelier. Yeah, and then there's a number of other group theoretical techniques we can use. We can say something about the groups, about the divisible elements or distorted elements, and so on. But yeah, instead of going maybe too much into group theory, I would like to rather explain what happens in arbitrary dimension. So if our, if not just for surfaces, but for higher dimensions. So yeah, generalizations to arbitrary dimensions. So the first problem is, I mean, what we constructed clearly only works in dimension 2 because we blow up points and we have this Tarski theorem. So already in dimension 3, we don't have this strong factorization theorem anymore. But even if we had it, it wouldn't work because we can blow up points, we can blow up curves, and then the things get quite messy. And actually, there are also some group theoretical reasons why this cannot work well, because in BR P3 we have GL3Z, and this always has to be regularizable. This has property FW, and then yeah, this gives us into trouble. So that's unfortunate. But what we can do is we can still construct cube complexes, but the only thing is this time we have to leave the beautiful world of projective varieties, but we have to work with non-complete varieties. So basically, okay, now we just look at X variety, not necessarily complete. Again, not necessarily regular, just over a field K. And now the idea is, okay, we have another factorization, which is kind of much more, I don't know, pedestrian than the one of Tarski, which is the following. So if we have here X and goes a birational transformation that goes to Y, so we know by definition of a birational transformation, this induces an isomorphism between open dense subsets. So basically what we can do is we just take X here, and now we reduce all the elements of the exceptional locus, and then we get here to U, where it is isomorphism, and then we just add here again. So we have two different ways in some way of embedding this U into X and into Y. And we basically will use this factorization now to construct cube complexes. So let's first construct the cube complex C0X. So X is our variety, and we construct the C01. So what are the vertices again of our cube complex? So the vertices are equivalence classes of marked pairs again. So we look marked pairs A and phi. Again, A is a variety and phi is just a marking from A to our variety X. It's a rational map. And now we say that two such marked pairs are equivalent if this map here, well, we don't say it's an isomorphism, but just an isomorphism in codimension 1, so pseudo-isomorphism. So yeah, because what we want to do, we want to only remove hypersurfaces, so closed subvarieties that are irreducible and of codimension 1. And that brings us to the definition of the edges. So if we have a vertex A phi, and here we have a vertex B psi, then we put an edge between those two that is also oriented. If there is an irreducible hypersurface D, subvariety of A, well, such that B psi is just the same as, or can be represented by A, where we remove D, and psi is just phi restricted to A, where D is removed. So for example, okay, we find the complex we constructed before, again, it's always as a subcomplex. Because okay, if we just blow up, if this is just a blow up here, then this is verified, because blow up, you can just remove the exceptional divisor, and it's something that is isomorphic in codimension 1 to the thing we started with. But we can also just take P2, for example, and we remove a curve, and then we get something non-complete, and then we connect it. So these are the edges. And now it's probably also already clear how to construct the n cubes. So here we just remove we remove several hyper surfaces. So if we have here a cube, and then let's say so here the highest point is like maybe something represented by A phi, and then we remove some hypersurfaces, and here it's just something where we removed all of them. And phi restricted to A without all these hypersurfaces. So this, yeah, this gives us again a cube complex. And again, we have that you can show that this cube complex is cat-zero. So C0X is a cat-zero cube complex. So again, we can use our whole theory about the cat-zero cube complexes to understand this cube complex. I mean, it's not so hard. It's not hard to show it in this case again, because actually, as it turns out, if you have finitely many points, so it's basically the cube complex from a cubical geometric point of view. It's not very interesting. It's just one giant cube. So in other words, if we have finitely many vertices in this cube complex, we always find a cube that contains all of them. But nevertheless, it's a cat-zero cube complex, so we can work with it. So again, what are the stabilizers and what is the distance here? Well, first of all, again, we have that the group of birational transformations of X acts by isometries on this cube complex, again, just by acting on the markings. And again, it's an isometric action, and again, it preserves the orientation. And now we can see that the stabilizer of a vertex represented by A phi. So this time it's not the automorphisms of A, but it's the group of pseudo automorphisms of A, so the group of isomorphisms in codimension 1. So it's birational transformations that induce isomorphisms in codimension 1. And then what is the distance? So the distance between A phi and B psi, so between two such vertices. Well, this is just the number of irreducible components of codimension 1 in the exceptional locus of phi inverse of psi, plus the number of irreducible components of codimension 1 in the exceptional locus of psi inverse phi. So yeah, it's again the same, like first, yeah, as I said, we remove all the irreducible components of codimension 1 until we have our U, and then we add again until we get to A, and till we get to Y, to B. So okay, again, we understand the distance, we understand the stabilizers, and now we can actually again summarize this in the theorem. So actually, if we look at the number of irreducible components of codimension 1 in the exceptional locus of f iterated n times, then this sequence is either bounded or it grows linearly in n. So if iterated, like either it has to be of linear growth or it is bounded. And again, like the one from Gerasimov, so a subgroup is conjugate to a subgroup of the pseudo-automorphisms of Y for some variety Y, if and only if this number of exceptional components, irreducible components of the exceptional locus of codimension 1 is uniformly bounded for all f in G. And then again, like we can find something like, okay, it's much weaker than algebraic stability, but either it is pseudo-regularizable, or we find model where if we iterate it, like the number of irreducible components of codimension 1 of the exceptional locus just grows, is additive. So this is like a nice observation, and it helps us to understand this dynamic of the exceptional locus. So how does it change if we iterate the birational transformation f? And actually, we can use these results to this theorem then to deduce some results about about centralizers of elements that are not pseudo-regularizable, and we can also use it to give some restrictions on degree growth of these transformations. But now, actually, I would like to continue the construction of cat-zero cube complexes. So first of all, like there's no, okay, what we will do is there's no reason to stop by with removing hypersurfaces, but we can also remove subvarieties of higher codimension. So this gives the cube complexes CLX. So we now just do the same what we did for hypersurfaces, but this time we add or remove subvarieties of codimension 2. So we get again a cat-zero cube complex C1 of X, but now BRX does not act on this cube complex anymore, because here the marking will just be isomorphism of codimension 1, but the group of these pseudo-automorphisms, so the group of automorphisms of birational transformations of X that induce isomorphisms in codimension 1, they act on this cube complex. And then we can just continue this business. So we can just more generally So we get a whole sequence of cat-0 cube complexes. So for all 0 smaller or equal to L strictly smaller than dimension of X. So we can construct a cat-0 cube complex CL of X with an action of the pseudo-automorphism groups of Lx. So this is just the group of birational transformations of X that induces an isomorphism in codimension L. Okay, and then we have so we have this, and this actually now we can prove various things by using this hierarchical sequence of cat-0 cube complex. So let's just give an example. So if we have a subgroup G of Urech that has the property Fw, then this is always regularizable. So that's actually a nice surprising result, maybe. So how does this work? It's not just the pseudo-regularizable, but it's actually regularizable. So the idea of the proof here is that, well, we know that it has Fw, the property Fw, so it fixes a point a vertex in the first cube complex, so in the cube complex C0x. So it is a conjugate to a subgroup of the pseudo-automorphisms, so in codimension 1 of Y for some variety Y. And now, okay, so it is in this group now, and this group now we know acts on the next cube complex here. So we know that G now acts on this C1 of X, C1 of Y, and then again it has to be conjugate to in sort 1 of Y to a subgroup of the pseudo-automorphisms, so the codimension 2 of I don't know Y prime, and then we just continue like that until we obtain that. So here they are always isomorphisms codimension larger and larger, and in the end it's automorphisms until we obtain that G is conjugate to a subgroup of automorphisms of Z for some variety Z. And yeah, that's the idea of the proof. So basically we have, yeah, and then we can do similar things we can show that divisible elements always have to be regularizable, or distorted elements always have to be regularizable. And yeah, it's basically just going from the large cube complex, and if the group is elliptic, then we can go to pass on to the next cube complex, etc. Yeah, so that's basically all I want to say. So that this gives, like, just to say this, these cube complexes, they give nice new tools to understand properties of groups of birational transformations in any dimension. And in some ways it's nice because it's like the first, let's say, nice or interesting geometrical spaces with an action of B or X for any dimensional X. On the other hand, it has also limitations because like the Vertex Stabilizers, they are really large. So it's automorphism groups of not complete varieties, and these can be very large, and they are not at all understood. So I think it's good tools to study groups of rational transformations that contain elements that are not pseudo-regularizable or that are not regularizable. But if all of them are regularizable, it becomes more difficult. So thanks a lot for your attention.
Thank you, Christian. Thank you very much. Let's upload. Okay. Thank you. Okay. Questions?
So what are the classes of groups in abstract terms, say solvable or whatever, that has a priori has this property FW?
The FW, yeah. So in general, it's basically the property T for groups. So it's the same as that's maybe well known. So for a long time, it was actually open if there are groups that have property FW but not property T. But actually, there exists some. But yeah, basically, so it's I think of something like rather rigid, like SLN set for n larger or equal to 3. But also, I think like SL2 set if you add like square root of 2, for example. So there, I think it's open. It's still open, but it's conjectured that maybe lattices of semi-simple Lie groups always have this property. Yeah, these kind of groups. So just think of like it's kind of like a rigidity property. Yeah, but it's not so easy to show that the group has this property.
Thank you, Christian. I have actually a small question. So, for example, do you have any explicit applications of these results, for example, for threefolds?
Yeah, so it's, I mean, explicit, not explicit. I mean, it's rather, yeah, I think it's rather implicit. So the applications you have, it's really like, okay, if you have something that's not pseudo-regularizable, then the degree growth has to be at least linear, or it's something like, if it's not pseudo-regularizable, then the centralizer, either it preserves the vibration, or the centralizer has to be up to finite index, just the element itself times a torsion group, or these kind of results. But I think it could be actually interesting to study the geometry of these cube complexes, for example, in dimension 3 or higher. Like we know, okay, the first one, the C0 of X, it's just one big cube. But after, if we go to smaller codimensions, it actually gets again a cube complex, which is not just one cube. So maybe that could be an interesting thing to do.
Okay, thank you.
So,
any other questions?
Yeah, there is a question. So how to compare this action on cube complex with the example which was studied by Lamy, Beasy, and Furter, when you deal with the tame automorphism group of
Yes. I think it's quite different. I think it's a priori rather unrelated. So I mean, their thing is much nicer. I think it's even a square complex that they construct. It's not just like ours is really infinite dimensional, so it's in many ways quite ugly. And theirs, I think it's maybe in a square complex. It's been a while that I looked at the paper. Or just like it's finite dimensional, so it's quite nice. And yeah, I don't remember. I did with valuations maybe at infinity of the of the tame of SL3C. So I think it's a different approach. It's more so direction of
okay.
Yeah, maybe.
Thank you.
Thanks, Christian. Any other questions to Christian? Okay, if not, let's thank Christian again. Thank you very much for excellent talk. Yeah, I stop recording and then we can chat.
Okay.